I think that's just how it is.
Okay, welcome back. I'm Clay. I'm going to be telling you about non-invertible symmetry, another recent development in this notion of generalized symmetry in quantum field theory, which you've been hearing already about from Hotot. And so today's lecture will be an invitation to non-invertible symmetry. We'll start sort of abstract from 10,000 feet, but hopefully by the end we'll latch on to one concrete example where we can cut our teeth. And then we'll build out from there to more direct applications in later lectures. OK, so I'd like to start with a question. And the question is sort of to restart from where Hotot has been talking. What should we mean by symmetry? So how should we define this term in quantum physics? And one answer that presents itself right away in quantum mechanics. So this is the quantum mechanics answer. And I should say maybe here, this caveat, I'm always going to be talking about internal symmetry. So there are space-time symmetries which are more general, but I'll be focused always on internal symmetry. So what should we mean by internal symmetry? So in quantum mechanics, what's our setup? We have a Hilbert space. And we have a Hamiltonian. This is basically it. And, well, what can we say? A symmetry, an internal symmetry, is an operator, U, with U, H equals 0. Definitely we all agree on this point. And actually, in quantum mechanics, we don't have much more to work with, so maybe we should just stop here. Now, I would like you to notice one thing already, that this is a linear condition. So let's call this equation star for the minute. So what I mean is that if we have U1 and they obey that equation, then trivially alpha 1 U1 to U2 also commutes with H, where alpha 1 and alpha 2 are any complex numbers. And in general, are unitary. Alpha 1 U1 plus alpha 2 U2 is not. Okay. So if you thought that symmetry was somehow intrinsically rooted in unitary operators acting on Hilbert space, bad news. You are wrong. Now, in quantum mechanics, there's really not much more to say. This is a very floppy condition, and there are lots of things that we might define, if that's all we use, that we might call symmetries. So it's not clear this is a very useful definition. So,
but we don't want to restrict ourselves to unitary as an extra constraint on our definition.
So the question is, why should do we want to restrict ourselves to unitary or anti-unitary? Well, that depends on it's useful to do so, I would say. So unitary symmetries are easy to identify. Anti-unitary symmetry, the time reversal, is also easy to identify. And what we're going to see is that it turns out that non-unitary symmetries, in that operators that commute with the Hamiltonian, are also going to be easy to identify if we open our eyes. So that's basically the subject of the lectures. OK, so answer 2, quantum field theory, which we're going to build on. So in quantum field theory, we, of course, have the Hamiltonian and the Hilbert space, but we have more structure. what's the more structure that I'll use? So I'm going to add ideas like locality and relativity. And we're going to see what that buys us. So the first thing is that we don't just have a Hamiltonian, we have a local operator, T mu nu, which is the energy momentum tensor. And instead of just requiring that a symmetry commute with the Hamiltonian, we will, as Hotat has discussed, require that it commute with the whole energy momentum tensor. So that's a kind of locality assumption. So this implies that U is a topological operator. So we're going to work with that. In a relativistic theory, we have more. And I'm going to focus on that now. So what can we do? So the green is on.
Couldn't see it.
Can people hear me in the back? Yes? OK.
I'm not worried about that.
OK. I can be even louder if necessary.
It's the recording.
I see. OK. All right. Good. So we're going to be in a relativistic theory. Yes, please.
I see the word topological here in the way Hotat has been talking about these terms, deformations.
Yes.
It doesn't change. By just commuting with the stress tensor, it means somehow the energy content does not change. So how are these things?
Well, but also translations, right? So T mu nu is the current not just for energy, but for translations as well. So that allows me to push the defect in different directions. Yeah.
So oftentimes the way I think about symmetries being useful in quantum mechanics is that they tell you something about the spectrum. But if we just have this commutation relation,
That's all you need. So I'm going to. Yeah.
equivalent to finding the spectrum.
So good. So the question was, you think about symmetry as being useful to find the spectrum. Well, it's a question of usefulness. So if you can identify an operator that commutes with the Hamiltonian a priori without diagonalizing the Hamiltonian, that's useful whether or not the operator is unitary. Right? If it's you have to first solve for the spectrum, then that's not very useful. Right? So it's a question of what can you identify without solving the theorem. Question.
Yeah, still about quantum mechanics. I thought it usually goes to say that like matrix elements should not change under a symmetry transformation.
So that is. Yeah, so the question is, what about Wigner's theorem? Well, Wigner's theorem just puts in that the matrix elements don't change, right? That's just assuming that basically the operator is unitary or anti-unitary. But if you asked what's useful for constraining the spectrum, like the previous question, then actually it's just this condition. Right? The preserving the matrix elements, that's something else. Preserving inner products, that's something else. We'll see. The proof of this pudding is in the eating. We got to find some non-unitary operators that commute with the Hamiltonian and let us do something interesting. Okay, but before that, I'd like to get you thinking about sort of what's the general structure of the answer going to look like. So in a relativistic theory, and this is where we're going to go beyond quantum mechanics, really, an operator U can also be a defect. So what does that mean? So we're going to place U on sigma times R in space times time. So sigma is just think of it some closed manifold in space where U sits, and then it just extends in time. That's the R factor. Okay. So maybe we could draw a picture. Okay. Here's space. This way is time. Here could be our sigma. And so U just extends along like this. Okay. Now, when we do this, we get something new. Okay, so when we quantize a theory with this U inserted, it modifies space, and so it defines for us a new sector of Hilbert space. Okay, and I'll call this sector HU sigma. Maybe curly H, distinguished from the Hamiltonian. Okay. So that's a new sector of Hilbert space. What is it in a familiar context? You're probably used to this. It just hasn't been phrased in such an abstract way to you before. So U is on the boundary of the red thing. So U in this example is an open is a cylinder that's not filled in. Okay, so just as a kind of a side example, let's say U is a zero form unitary symmetry, ordinary global symmetry. We could even say for U1, and we have some Lagrangian with fields phi. And if I conjugate phi, I get a phase. So I have some fields transforming in representations of the symmetry. So what will this twisted sector look like? So we're going to choose coordinates. Such that sigma is the locus where x1 equals 0. That's my local definition of the coordinate x1. It's a zero form symmetry, so the operator is codimension 1. So I just need to set one condition on the coordinates. How do I get HU sigma? I impose singularities on the fields. So what's that singularity going to look like? Well, it's the limit as x1 goes to 0 from one side of phi of t xi equals e to the I alpha times the limit as x1 goes to 0 from the other side of phi of t xi. So it's twisted boundary conditions for your fields. Right? You're familiar with this when you do study a chemical potential, or maybe when you talk about periodic or anti-periodic boundary conditions for fermions. You've seen these twisted sectors before, these Hilbert spaces. It's something we can generally define given an operator. Okay, so a key point. So we're done with the aside. We're going back to the general discussion. The consistency of this Hilbert space is a nonlinear constraint. On U. This will give a very rigid structure to what we mean by symmetry, demanding that all these Hilbert spaces exist. Okay? So, yes?
The Hilbert space is just when you quantize the fields with this boundary condition.
Exactly. So the question was, what's the Hilbert space? It's quantize the fields with this boundary condition in space. Yes? More questions before I keep going here? Yes? How is it different? Well, what I'm going to tell you is that given, maybe it will become clear soon, but essentially the logic of where I'm going is that given any operator, we're going to be able to define, we're going to insist that we be able to define these Hilbert spaces for different choices of sigma. And that's a constraint on what U can be. So we'll see that soon. Yeah?
Your example seems
seems to not require that this is a symmetry. Some operator that uses some sort of boundary conditions. Is that important at all here? For a consistent Hilbert space or something?
Good question. It is Oh, the question is it important that this is a symmetry action? The fact that it is a symmetry action will enable me to define, it's kind of in the definitions that I'm going to lay out, but the fact that it is a symmetry action is what's going to enable me to define these Hilbert spaces. Now, there are other defect Hilbert spaces that are not based on symmetry. So the concept of a defect Hilbert space is more general, but we are going to work in the specific case of a symmetry defect.
Can I ask a question?
Yeah.
Just for clarification, this is totally different than when we say charge sector and uncharged sector. It's a totally different thing.
This is different, yes.
I guess this operator U is also topological.
So right now, so the concept of a defect is far more general, right, than just topological defects. But this defect has the interesting feature that the Hilbert space, I can wiggle sigma a little bit, and it will not respond.
Yeah, I guess I was curious how to see that from here, where we're imposing a boundary condition at this cylinder. We could impose that at a wiggly surface. And how do you see that?
You will have to use the fact that there is a conserved current to move the move the surface. It's equivalent to this Noether's theorem argument that Hotat has given you. Yeah.
So why is it important that the is relativistic again here? Can I do this?
Oh, well, the question was, why is it important that the theory is relativistic? So I'm rotating the defect, right? So initially I had an operator. That's a concept that exists at a fixed time. And now I'm telling you that we're going to insist that these operators that exist at fixed time, we can also rotate them and define them as being extended in time. And then that gives us the modification of the Hilbert space. In a non-relativistic theory, we may not be able to do that. Okay, I lost my notes. Okay. Oh my gosh. Yeah.
For the rotator, you mean the Lorentzian transformation?
Yes?
But I think the Lorentzian transformation cannot transform the space like slice to a time-like slice.
It only cut the time-like slice transversely. Okay, good. All right, so let's, I'm going to ignore further questions for a little while. Okay, so this consistency of this Hilbert space is a nonlinear constraint on U. And I'd like to show you some of that. So there are two mathematical operations on Hilbert space. So the first is direct sum. Okay, so direct sum, Hilbert space is a vector space, so given H U1 sigma and H U2 sigma, I can take their direct sum. And I will define this to be a Hilbert space associated with the defect U1 plus U2 on sigma. So this defines addition. Let's come over here. This will define our addition operation on defects. So U1 plus U2 makes sense. We're talking about logical defects here. In particular, n times U, which is defined as U plus dot 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 plus U n times, this exists if n is any natural number. But alpha times u for general alpha complex does not make sense. So we already see a big difference here. When we talked about operators acting at fixed time, and that was all the structure we had, you can obviously rescale an operator by any complex number. That's another well-defined operator. But if you insist that this operator can also define a reasonable Hilbert space, then you're stuck with integers. What was the question, sir?
Have we restricted ourselves to symmetry defects?
No, not yet, but I do not wish to like add footnotes of throughout. So in my discussion, you can assume that I'm doing symmetry defects.
Can you add up like two Hilbert spaces with, for example, the same U but different sigmas?
We are not going to try to do that. You could try to do that, but I'm going to try to give. The question was, can I add Hilbert spaces for different sigmas? You can definitely define the direct sum operation, but what I'm trying to show you is operations that exist on a fixed sigma, on a fixed spatial modification.
Yeah, so this sigma is somehow like just a picked arbitrarily? Or?
That's right. Sigma is picked arbitrarily, right? So part of the constraint is that this Hilbert space has to make sense for any sigma.
Okay. So
Right?
it's just the configuration space of some field configuration with singularities on sigma.
Right, and it has to make and this Hilbert space has to make sense for any sigma. That's the strong constraint. Okay, so good. So that's our first operation on vector spaces or Hilbert spaces, and it gave us an addition on defects. Okay, the second operation, tensor product. Okay, so if I have HU1 sigma, I can take its tensor product with HU2 sigma, and I define this to be my multiplication operation on defects. Okay. This one we can give a nice picture for, which should already be somewhat familiar from Hotat's lectures. So this is parallel fusion. So I can take, here's sigma, here's U1. Here's another copy of sigma just parallel transported away, U2. And then take parallel fusion. And put these defects right on top of each other. And here is U1 times U2. Now, notice we're in the topological universe here. So this looks like it could be an operator product with lots of singularities, but in the topological universe, there are no singularities. This length scale here is immaterial. So there are no singularities. And this tensor product makes sense. I'm kind of combining the degrees of freedom for both. That's why I get a tensor product when I bring them close together. Yes, question?
U1 and U2 don't commute. The left-hand side is commuting.
The left-hand side is not necessarily commuting. Well, sorry, I have to define sort of left versus right fusion. Kind of depends on the. Sorry, what exactly is it? Maybe I don't understand. You can have symmetries that don't commute.
Yeah, but normally, like in the tensor product, it doesn't matter if the ordinary right U1 and HU1 and HU2.
Well, I have a limit. Okay. Yes, it is true that I am cheating a little bit. So this is actually a very good question. Maybe come ask me about it in detail afterwards, because it will derail us a little while. Yeah.
In one of the lecture, we were doing some fusion where at some point they would join and then they were like mutually separating and joining. Would that happen when sigma 1 and sigma 0?
Yeah. So Hotat was talking about how you could fuse them partially, and then the orientation help you keep track of the ordering. And here I'm also kind of implicitly not telling you what's going on with the orientations. Yeah. Yes.
Does the Hilbert space dimension actually increase under this transformation?
But they're usually they're often all infinite dimensional. So no.
But it's still like should mean like a Fock space or something.
How you construct these Hilbert spaces depends on the particular example, but typically they're infinite dimensional. Question, yeah.
So these operators U were already belong to the algebra of operators acting on the full Hilbert space of the theory, right?
Yes.
So why are we now would we have to ensure that these new operations we're defining on them are compatible with the previous ones? They already had addition and multiplication, right?
That's a great question. So I was actually about to write that. So yeah. Yes.
So like, physically, it seems like that we're kind of overcounting the degrees of freedom when we do the tensor product. I don't know, like both these.
No, decoupled. The question is, are we overcounting degrees of freedom? Decoupled systems, the Hilbert space is always tensor product, and the fact that these are close and far apart is a fiction. Right? Topological things. So if I spread them very far apart, they're clearly decoupled, and then the degrees of freedom should definitely be the tensor product.
But like the left-hand side. Yeah. Well, no, it seems like you get two sides right.
Okay, let's keep going. Okay, I do want to get to the actual example if possible, so let's see if we can do that. Abstract stuff is always the most confusing. In a particular example, it will all be better. Okay, so as was just asked, the operations plus and times have a dual meaning. Okay? So there's the operator meaning that's acting on the regular Hilbert space. And there's the defect meaning, where things are extended in time. So here, plus is just regular old addition. U1 plus U2. Okay. So these are operators, big matrices acting on Hilbert space, and we're talking about regular addition of them. And here it's direct sum. So HU1 plus HU2, suppressing sigma. So the question was, someone asked, how do I see that these are the same, that these are compatible? Okay, so this is actually my first exercise for you. It's just unpacking the definitions that I've given you so far. It is mostly just language to see that these are the same. Okay, and then there's the times. So this is multiplication of operators, ordinary old multiplication. And here it is the tensor product. And this one is more transparent because it just depends on which way you define time in this picture. So if I define time this way, then it's clear that it's operator multiplication. And if I define time this way, then it's clear that it's the tensor product. So the second one is actually easier to understand, the compatibility of the operations. The first one requires a little more thought.
If I take one of the U's there, product to be the identity, I have the tensor product of the Hilbert space with standard boundary conditions, one of the twisted ones, being equal to a single Hilbert space with twisted boundary conditions. Don't I?
Yes. The identity defect, so that's a general property. The identity defect fuses with any other defect to give you back this defect. That's kind of a general algebraic structure that we have. Okay. Good. Okay, so these are the two operations that we have. We have product and sum. And I'd like to get out of the realm of abstract things as soon as possible. So let me do one more abstract thing. So a topological operator, U is called simple if it is not a sum. Not a sum of other topological operators. So that means that U is not equal to U1 plus U2 for any U1 plus U2, for any UI other topological operators. And this is well defined, I should say. It's a well-defined notion. Once we're outside the dimension where we had this problem in quantum mechanics. So in quantum mechanics, we could take general linear combinations. There seemed to be nothing restricting us. So this is well defined if the U's are all extended. So lines, surfaces, etc., but not points. Okay. So some examples of simple operators. So say 1p, the identity extended operator. Of dimension p greater than 0. This is simple. And now I need to put a little asterisk here about no universes. If you don't know what that means, just ignore it. And similarly, invertible or unitary extended operators. So these UGs that Hotat has been telling you about, these are also simple. And I invite, this is again, another simple exercise to check that you're understanding the words. There's not really much content to it other than the words. Yes?
If we need the caveat no universes on the identity, but you're saying, do we also need it on?
Yes. So this caveat applies to this distinction, this board. That's an annoying caveat. Yeah. Okay, so in general, the complete collection of simple operators of a given dimension forms something like a basis. Some algebraic structure that's similar to a basis. Okay? I'll call it a basis. So that is not a technically correct use of that word. What I mean by that is that if we have some ui and uj, and we multiply them together, we could try to expand the result. Where here, I, j, k label simple operators. So now these labels don't have any reference to a group. We're outside that context. We're just talking about algebraically what is the structure we expect. Right? There's a notion of being kind of primitive or simple. You can't split into a direct sum. And given that, we can try to take the collection of all simples and any product re-expand into simples, where here, of course, the nijk's will have to be natural numbers because we can't have arbitrary coefficients. So this is kind of the starting point equation to invite you to consider the algebraic structure of non-invertible symmetry. More than one term on the right-hand side this is the hallmark of non-invertible symmetry. Right? That's definitely beyond a group. In a group, when you multiply two things, you get a unique third thing. Right? Here we're contemplating the possibility that there are some kind of extended operators with some abstract set of labels. We don't know what they are, but the fusion of two of them gives you in general a sum of others. Okay, so that's the algebraic generalization that you need. Yes?
So,
go ahead, you. Yeah.
So is it equivalent to say that there is a non-invertible symmetry for operators or a Z-mod? Is that
Or what?
or a Z module?
A Z module. So the question was, I think the spirit of the question is, what is the underlying mathematical structure here? The answer to that is something like a fusion category or a higher fusion category, but I'm not going to define all of that for you. I'm going to quickly now pivot into real examples. Go ahead.
No, I'll just ask you that because it was about the categorical stuff that you're saying.
Right, so I have definitely not told you sort of all the algebraic structure. All I have told you about is parallel fusion. What about intersections? What about manipulating intersections? There's lots of things we can do here. So far, I've just told you about parallel fusion and direct sums. That's a very limited set of things, but it's enough to get us started. Yeah, in the back. What is the definition of U1 times U2? Yeah, so the definition is what's on the board here. You could say that if you have two topological defects, you just quantize the theory with them split a little bit apart. And that's the whatever you get, that's the definition of the Hilbert space for U1 times U2. Okay, so yeah. No, not in general. So the question was, is this sum finite? So it kind of depends on where you're going. There are examples in the wild that are finite, and there are examples in the wild that are where the sum is infinite. If you want to do something like generalize a finite group, then the sum will be finite. Right? So in the group case, you would have had one simple defect for each group element. And so if that was a finite group, the labels would be finite. If it's an infinite group, the labels would be infinite. Yes, question?
Two defects distant L apart, then I should quantize my field to using the classical solution that satisfies the twisted boundary condition. That depends on the distance length L. But then now I change the distance, say, to L prime, which is different, and my classical solution changes.
Yeah, so the question is about the dependence on the distance in this product. So this is where I'm heavily using the fact that everything is topological in my lectures. Because of that, this distance here is not a relevant variable. Right? So, but if we were to discuss Hilbert spaces of more general non-topological defects, then we would become sensitive to that. We would only expect the tensor product in the limit where the defects are very far apart. Okay. Good. So this is enough to sort of whet our appetite to consider this possibility. But as with the general discussion of sort of what's possible, it's really what's useful. So the question is, what examples can we find of this structure? So for the rest of my lecture, we're going to talk about sort of the first non-trivial example of this. And therefore, we're going to see that there really are non-invertible symmetries out there. Okay. So the first example, very not an example, but really something that everybody ought to know. So now we're going to exit the realm of the abstract and go to the concrete. We're going to do the 1 plus 1D Ising model. Okay. So what is this theory, if you've never heard of it? It's a critical point, so a conformal field theory. And there are lots of definitions of it. But one way to start is to think it's a scalar field theory plus a quartic potential. So this is where we start. We start in the UV with some real scalar phi. We turn on a quartic. We tune away the quadratic. And we flow to the infrared until we hit some non-trivial conformal field theory. That's the Ising model. This is really the first non-trivial example of quantum field theory. It can be solved exactly. I'm not going to actually solve it for you, but I'll present the structure of the answer so that we can see how it works. So this is an abstract CFT. That's how I'll think about it. It's characterized by local and, of course, extended operators. And the hero for us will be the extended operators. Since we are in 1 plus 1 dimensions, or 2 Euclidean dimensions, the only extended operators of real interest are lines. So all the topology, et cetera, is going to get a lot easier very soon. OK, so let's make a little table of the operators and their properties. OK, so it's a 2D conformal field theory, so we can think of everything in terms of Virasoro primary local operators. So that will be one column. We'll also have here the scaling dimension and the spin, which I'll group as usual into a pair H and H bar. Those are the eigenvalues of L0 and L0 bar, if you know something about 2D CFT. And then, just to help you get some intuition, what is the UV field theory interpretation of each of them? So in terms of that scalar phi that we started with. OK, so it's the identity, scaling dimension 0, 0. And I don't even need to write anything here. The next one is called sigma. There are various different names in the literature. I'll call it sigma. Sometimes called the spin field. It's scaling. And you should think of this as the infrared avatar of phi. So we start with a scalar field, and it flows to something at long distances. It flows to this operator. And the last one is epsilon, sometimes called the energy. Its dimension is 1/2 and half. This is like phi squared. These are each Virasoro primary operators, so it contain descendants that are an infinite list of other operators in the theory, but these are the primaries. These are the ones we need to keep track of. Yes?
Phi is not Virasoro primary in the UV, so d phi is the Virasoro primary, so why is it not d phi?
Why is it not d phi? Well, the kind of non-compactness of phi is going to get hard cut off by this phi to the 4th potential. This is just to help you get some intuition as to what should be charged under what symmetries. Yeah?
Why is it called spin field if the theory is scalar?
Why is it called a spin field? So, like I said, there are different ways of realizing this model. One way is as a statistical model where each lattice site has a Z2 spin, Z2 fluctuation. Then the local variable is a spin, and that's this one. Good. Okay, so maybe you might ask also, if you're trying to get some intuition, why no phi cubed? Why did it stop? Why did the list get truncated here so dramatically? One way to think about that is that the UV equation of motion, this is again just for intuition, is that d squared phi is like phi cubed. So phi cubed is a descendant. So we don't need any more powers of phi. Okay, so now, conformal field theory is characterized not just by its list of operators, but also by the operator product expansion. I will give you a cartoon of that. The cartoon is called the fusion rules. You can think of this as an OPE where I don't tell you the coefficients. I just tell you what operators appear in what multiplication. So epsilon times epsilon is 1. Sigma times epsilon is sigma. And sigma times sigma is 1 plus epsilon. So you should, again, think of this as a cartoon for what the 3-point functions are. So, for instance, this sigma sigma epsilon 3-point function is non-zero because of this term. Okay. The final thing I will briefly mention is the state operator correspondence. So that implies that associated to each of these local operators is a state. 1, sigma, and epsilon. In H, what's this Hilbert space? We've been talking about lots of different Hilbert spaces. This is the Hilbert space on a circle. Okay, so that's all you need to get started thinking about the local operators. But our discussion here is really about the extended operators. So let's get started with those. So remember, we put in that any extended operator U, we want it to commute with the stress tensor. And in a 2D CFT, the stress tensor generates all the Virasoro algebra. So this tells us that U is characterized completely by its action on primaries. Okay. So we will write it this way. We introduce three numbers characterizing any U. U is going to be a line operator for us. So there'll be an eigenvalue of U acting on the identity state, an eigenvalue of U acting on sigma, and an eigenvalue of U acting on epsilon. As an operator, if I only care about acting at a fixed time, any AI are allowed. Constraints on the AI come from thinking about U as defining a twisted sector Hilbert space, a new sector that we're going to talk about now. Yes?
I mean, how do you know that the U does not change the sector?
Great question. The question was, how do I know that U does not mix these up? Right. And the answer is that all of them have different energies. Right? These eigenvalues are different. So it cannot. Yeah, exactly. Right? It commutes with the Hamiltonian in particular. If I had a conformal field theory where there were multiple primaries of the same dimension, then I would need to contemplate the possibility of mixing them. Okay. So our constraints will come from HU. Okay, so since we're in such a low dimension, all these Hilbert spaces and everything become very explicit. In particular, you could ask about the state operator map for these interesting defect Hilbert spaces. Okay, so let's do that. So here, is my space-time. So this is space. Here is time. Okay, and here is my red chalk. So if I don't put anything in space, then we're back to the standard state operator correspondence. But in this case, we'll modify space by putting U at one point and extending it in time. So this is giving us a state O that lives there in this Hilbert space associated to the defect U. Now, because we have conformal symmetry, we can think of this Hilbert space in radial quantization, right? Where I think of these as concentric circles going out from the origin. In that case, what do I get? Well, O sits at the origin. But now, there's this U tail attached. So this is a twisted sector operator. So an ordinary local operator is the special case where U is the identity line, right, where we don't put anything there. And then there doesn't exist this tail here. This case, we have operators which have these top tails attached. So if I think about them in correlation functions, they will not just depend on this position, but they will also depend weakly on the presence of this line. For instance, only topologically. So for instance, maybe you've seen correlators with branch cuts. The branch cuts can often be interpreted as these U's. There was a question.
Does one have to be careful that the state operator correspondence holds in the presence of U?
Yeah. The question was, why does the state operator correspondence hold in the presence of U? I am insisting that my U preserve all the conformal symmetry of my problem by this condition. So I'm free to still do the conformal transformation that generates the state operator correspondence. Yes?
I guess to try to just make it specific in my head, since we're in 1 plus 1D, the 2-point correlation function with the sigmas, if I think of them as phi's, should be a log. And that would have
The sigmas, if you think of them as phi's, they will not have, these are ordinary local operators. They will have no branch cuts. That's the kind of failure of thinking of phi in the UV, right? So a free field has a log correlation function, but we have a strong quartic interaction. Yes?
Does everything in this picture live in the boundary of the cylinder?
Nothing is inside the cylinder. We're in 1 plus 1 space-time dimensions. So space is this circle marked by this one point, and time is just this line. OK, so consistency of these Hilbert spaces is going to fix these eigenvalues. How? What would you actually have to do? I'm not going to do it explicitly, but I'll outline the argument. And this will be my first real homework problem, not just to check the words, but a real kind of grind through something, as Luca said, between 2 and 4 a.m. in particular. So, OK, so concretely, the AI are fixed by modular invariance. To use this, you need to know the partition function of the Ising model. That is a well-known thing that you can look up in many textbooks. Let's see how we would use it. OK, so we'll consider a torus. I'm going to do modular transformation, so I need a torus. So you could think I'm just going to compactify that time direction. So here's my torus. This side is identified with this side with this side. Here is tau. So this is a torus with modulus tau. Okay. And we will consider having u inserted here. So here's u. So partition function on this configuration with the insertion of u has 2 interpretations. Meaning number 1, star sub 1. Here, we think of this direction as time. This direction is time, then u is acting at a fixed time. Okay. So then we have a trace over our standard Hilbert space on H1. What's in the trace? Well, u is acting at a fixed time. Doesn't matter which time because it's conserved. So we just put it somewhere. And then we have our standard e to the 2 pi I tau h minus c over 24, e to the minus 2 pi I tau bar, h bar minus c over 24. So that's a function. Interesting function of tau and tau bar. It can be worked out explicitly. Notice that it is fixed. So here u is acting at a fixed time in this interpretation. And it's fixed by the AIs. Right? Because the states in this Hilbert space include these and their Virasoro descendants. So if I want to write an explicit formula, it will be some function of tau and these AIs. So the H is BL naughts because I put the C over 24. H is an, I'm talking, okay, fine. Yes, I'm abusing notation. Let me just not introduce L and L naught. H are the eigenvalues, H is the eigenvalue of L naught, H bar of L naught bar, assigned to any state in this trace. Yeah. Okay, so that's interpretation 1. Perfect. Interpretation 2 is where we view U as extended in time. The partition function doesn't have that knowledge in it, right? The partition function just depends on the torus, and U is on a circle. It doesn't know which way you define time. That's why we're going to get an equation here. Okay, so I view U as extended in time. Now the trace is on this twisted sector Hilbert space. Okay, and because I have rotated space and time, I have done a modular transformation. So I have a new tau tilde, which is minus 1 on tau. This is the modular S transformation. Okay, so that's again a formula that I can work out, and it must be equal to the other formula after I set tau tilde to be minus 1 over tau. Okay, this must yield integer degeneracies. On HU. At each energy level, in each spin, we have to have integer degeneracies. Okay? That requires some kind of miracle, right? If you think about what this function is, it's going to be some complicated modular form. I'm going to do a transformation on it, and I want to re-expand it and get, again, integer expansion in dual variable. Okay? That's some kind of miracle. And indeed, it is kind of a miracle that it works for any AIs. So it fixes AI, 2, 3 simple cases. I'm using simple in the same sense I was using before. 1 second. So this is not an exercise, but more like a homework. It will take you more than 1 minute to do, but it's still doable. Yes, question?
So the operator now is no longer extended in time. So it's now extended in time. So should we still insert it in the trace, or what's the quantity we're computing?
Yeah, we're computing a trace of. Here, I'll write it. Yeah, sorry. The question is, what are we computing? So it's a trace on HU. This is where U appears now, of e to the 2 pi I tau tilde h minus c over 24, e to the minus 2 pi I tau tilde bar h bar minus c over 24. So now there's no explicit insertion of U. It's just here. Okay, and this function has to be, first of all, have integer degeneracies when I expand it out. And second of all, has to be equal to that function when I do the modular transformation. Yes?
Are there additional constraints on the AIs that you get from the full symmetry group of the doors?
No, this is enough. Yes, that's a good question. Are there additional constraints that I get from the full symmetry group, in particular T? No, this is enough. T is an interesting story, though, so come talk to me about it. Question in the back. Suppose you don't know it. So you know this function, right? This function, you just need to know the local operators and these AIs, which characterize how this hypothetical U acts on the states. Okay. Now you do the modular transformation, and you re-expand in this new modular variable, and you say, for which choice of the AIs do I get integer degeneracies at each energy level?
So
Yeah. Yeah, in this presentation, that's how it works. There are other ways to get what HU is, but this is a way to see the answer. OK, so this equality of interpretations between *1 and *2 fixes. I need this. This is perfect. Okay, so we need a new little table. This fixes the AI. OK. OK, so here's the line. U. And I guess we need one more column. OK. So here will be A on the identity. Maybe I called it A1. Here will be A sigma. And here will be A epsilon. So 1 is identity, boring, but I'll write it anyway. Identity line. So this is 1, this is 1, this is 1. Nothing interesting has occurred. A second one is something we should have expected, a Z2 symmetry. The Ising model has a Z2 symmetry. We defined it by a quartic scalar with no odd terms in the Lagrangian. So there's a Z2 symmetry, so we better find that. And we do. And how does it act? It acts as you would expect. So it acts on the identity as nothing. Remember, sigma is the infrared avatar of the UV field phi, so it acts here by -1. Epsilon is the infrared avatar of the UV field phi squared, so it acts here as +1. OK? So far, nothing interesting. Finally, something non-invertible, often called D. What are its eigenvalues? Square root of 2 on the identity, minus square root of 2 on epsilon, and here's the non-invertibility, 0 on sigma. Okay, so this is something we discover just doing the modular transformation. So eta, as I said, implements the Z2 symmetry, which we expected. It's D that is surprising. Okay. Yes, question?
Sorry, aren't we discovering D? Is it? I thought the
Good. So the question is, what's the logic for the discovery of D through modular transformation? So this function you can compute given only the local operators and the proposed eigenvalues, A1, A sigma, and A epsilon. That is a known function of tau and the AI. Then I do a modular transformation, and I demand that the AI are such that when I expand in tau and tau tilde bar, I get integer degeneracies at each energy level. That is an extremely strong constraint on the AIs. Okay? It fixes them to be sums with positive integer coefficients of these three possibilities. Question in the back, yeah.
How D acts on phi?
How D acts on phi. I will try to tell you how it acts on these operators. If your question is how is D defined in the ultraviolet, it need not be there. Right? It's a symmetry of the critical point. Yes?
So what does D mean? Is there like a physical sort of meaning to D?
Good. So one physical meaning to D is it's the consequence of Kramers-Vonnier duality. It's there because of that. We will get there slowly, maybe. It depends on how many more questions there are. OK, so D is more surprising. What are the implied fusion rules? So remember, I advertised that there's this fusion structure. Okay, well, we can read it off just from these eigenvalues, right? This is telling us how D acts on the Hilbert space. Okay. So you can see that eta times eta is the identity. Unsurprising for a Z2 symmetry. You can also see that eta times D is D times eta is D. What I'm doing here is I'm just multiplying the eigenvalues and seeing what I get. Okay. So far, nothing too shocking. And here's the money equation. D times D. This one is 1 plus eta. So it's D that is, again, non-invertible. And we see that at the fusion rules and at the eigenvalues. OK. The last thing I want to tell you about is, yeah.
How do you know that it's not 1 plus 2 eta?
How do I know that it's not 1 plus 2 eta? Well, let's read the eigenvalues, right? So D times D, this is a 2. And I have to get here, I have to add these with integer coefficients, right? Here I have to get 0. So these coefficients have to be equal, right? So that already answers your question. Here I have to get, again, 2. So I, again, have to add them with. OK, last thing. So we've now seen that non-invertible symmetry exists in the wild. Even in the simplest quantum field theory, it's there, in the Ising model. But what can you do with it? Why do you care? Right? Is it just some mathematical artifact, or can it explain something? OK, so that's, in a sense, a lot of the subject of future lectures. But I want to give you one thing to latch onto before lunch, which is selection rules. OK? So eta, we know what selection rules eta implies on correlation functions. Eta implies that correlators with odd numbers of sigmas vanish. Right? That's the standard Z2 symmetry on the Z2 charge thing. But what about D? What's that good for? So to make that more shocking, let me show you a kind of puzzle that you could have read off from the cartoon of the OP coefficients, the fusion rules that I showed. So kind of puzzle, you might ask, is how can you understand the following? Epsilon, epsilon, epsilon is actually 0. But epsilon sigma sigma is not 0. So when you see something like this, you say, aha, there should be another Z2 symmetry under which epsilon is charged. Not so, though. Here's an correlator with an odd number of epsilons, which is non-zero. So how could you know that that is going to be the case? And we'll see that this actually follows from the selection rules implied by D. So our answer is going to be to use D. OK? So we know that D on epsilon is minus root 2 epsilon. And we know that D on 1 is plus root 2 on 1. So we're going to introduce a kind of graphical calculus to manipulate those formulas. In particular, this one to start with just says that if you have an empty loop of D with the identity operator inserted, so the identity is no insertion at all. Actually, maybe I'll start drawing this in colors. Here's D with nothing inserted, that this is square root of 2. So that's this equation written. OK. I beg your pardon for 5 minutes, just so I can get to the conclusion of this thought, and then we'll stop. OK, so now let's do it with epsilon. So here is D, and here is epsilon. So of course, we know that this is minus square root of 2 epsilon. That's just that equation written graphically. And this is also equal to minus epsilon, and then I'll put d not surrounding anything, right? Because an empty loop of d costs us that square root of 2. So this you can think of as corresponding to that factor. Okay? Now, if I want to think of this as a local rule, right? A local rule for what happens when I push d past epsilon, it means the following. So if I have here d, and here is epsilon, that this is equal to minus epsilon with d on the other side. And the rest of d can be contracted into a loop. Right? So however you close this loop, this will be a consistent equation. Right? So that's the local rule that follows from this. Okay, so that's enough to see the selection rule, right? As far as epsilon is concerned, d is trying to be a Z2 symmetry, right? So more concretely, how would you derive a selection rule? So imagine you have 3 insertions of epsilon. This is on the sphere. So we're considering 3-point epsilon on S2 or the plane. So here's my correlator. I won't draw you the sphere, but you can imagine it's closed up at infinity. So the first thing I do is I insert. I keep these operators fixed. I'm only allowed to do topological manipulations to derive selection rules. The position of the epsilons is fixed throughout. Right? So first thing I do is I nucleate a little bubble of d. Now that doesn't quite cost me nothing. It costs me that square root of 2 that I put there. Right? So I have to divide this by square root of 2. These pictures are equal, though. What that means is that they're equal in correlation functions, right? Which is what we're manipulating right now. Now I grow the bubble. I grow the bubble, and I want to grow it in particular past the epsilons. Each time,